Lina madam, YouTube is already joined. No? We started. Okay, okay. Then we can start then. By that time. So we can start then, and by that time people may join because some of them may be on YouTube.
Okay, sir. Thank you, sir. Today, on this illuminated morning, we have our first lecture on memory of Professor H.C. Pradhan, and it's an online lecture. On this event, I welcome our speaker, Dr. Kishore Kapali. I welcome the IAPT authorities, life members, EC members, and the audience. I welcome one and all. Now, at the beginning, I welcome Dr. Shamla Bojani Madam to introduce IAPT SRC 08B. Welcome, Shamla Madam.
Hello, good morning, everyone. Thank you, Sushmita Madam. Before going to the introduction to RC 8B, I would like to talk about Dr. H.C. Pradhan, in whose memory we have arranged this lecture series. Dr. H.C. Pradhan was a well-known personality, not only as a physics teacher, but as a frontline active member of many institutes, mainly in the field of education. He was involved in research in the areas of nuclear physics, physics education, mathematics education, and science education. Dr. Pradhan retired in July 2011 as a senior professor and center director of Homi Bhabha Center for Science Education, which we know as HBCSC, a part of TIFR. He led HBCSC's program of developing higher secondary laboratories, which contributed to India's participation in Olympiad. As an award-winning author in Marathi on science, Pradhan sir has written more than 100 popular science articles, and as a sort of the speaker in the areas of education and science, he has given more than 100 lectures and radio talks. He taught, besides undergraduate courses in mathematics and physics, courses in ethics of science, history and philosophy of science, and communication in science and technology. He was vice president of Marathi Vignan Parishad for 8 years and editor of their monthly magazine for 12 years. Professor Pradhan's contributions to the Marathi Vishwakosh are particularly noteworthy. In March 22, he received the prestigious Goda Gaurav Award for lifetime contribution to scholarship in science from the Kusumagraj Foundation, Nashik. Earlier, in April 2018, he was given the Marathi Jeevan Gaurav Award for Manohar Vichare Foundation by Manohar Vichare Foundation for his work in science education. He chaired the National Experts Advisory Committee of National Council for Science and Technology Communication, that is NSCTC, which is a part of Department of Science and Technology, Government of India. This committee oversees children-centric science programs like National Children's Science Congress. He was also a member of MKCL Strategic Advisory Committee. MKCL is Maharashtra Knowledge Corporation Limited. He was a fellow of the Maharashtra Academy of Sciences. Dr. Pradhan was president of IPT, that is Central IPT, from 2013 to 2018. He was instrumental in starting the Sub-Regional Council RC8B of IPT in 2000 and was the first president of this sub-council. He organized various activities for RC8B and brought many physics teachers and students together for improvement of physics teaching and learning in Mumbai University. Everyone who got a chance to work with him, I'm sure, has benefited a lot in some or other way. On behalf of IPT RC8B and my personal behalf, I pay my tribute to Dr. Pradhan. Now I would like to tell you a little bit about the activities of IPT RC8B. The central IPT is divided in number of regions, each having a regional council. RC8 is a regional council of Maharashtra. We have a sub-regional council under RC8 as a Mumbai Sub-Regional Council 8B. We do conduct some activities regularly, one of which is a summer school for undergraduate students where main focus is on solving problems from various branches of physics. We also focus on workshops for senior as well as junior college teachers. A career guidance lecture for class 12 students, workshop for junior college students on theme-based experiments, experimental competition, essay competition are also our regular activities. Apart from such regular activities, we do help different colleges in organizing workshops or seminars on various themes as per their needs. We do arrange online lectures. Professor Dharkar Memorial Lecture Series was organized online. Now we are also planning to focus on school level physics teaching and learning. Recently, Konkan area, that is Ratnagiri and Palghar, are attached to RC8B. So now we will come to the first lecture of our new series, which is in the respect of Professor H.C. Pradhan. So I'll hand over my mic to Professor Bhole to introduce the speaker for today's lecture.
Good morning all. I welcome the President of RC08 Maharashtra, Mr. Professor Mahesh, all live members and dear participants. I am very much delighted to introduce the today's speaker, who happens to be a student of VZ Vaze College, where he has graduated in BSc Physics. After BSc Physics, he joined MSc program at IIT, and after completion of post-graduation, he also joined the training program at PRL, Ahmedabad. He received his PhD in Physics from Texas A&M University in the area of theoretical quantum optics. He has held postdoctoral appointment at Princeton University and the prestigious National Research Council Research Associate position at NASA's Jet Propulsion Laboratory, California Institute of Technology. His thesis research was centered on developing fundamental theoretical understanding of new state of ultra-cold matter that is termed as Bose-Einstein condensates. His theoretical investigations on coherent excitation of vortices in Bose-Einstein condensates was realized in experiments by Nobel laureate William Phillips. Using the tools of quantum optics, which involves study of interaction between light and matter at the microscopic level, Dr. Kapale is currently focusing on quantum information science, which is a new paradigm in information processing for development of better, faster, and more secure quantum technologies. Recently, Dr. Kapale has been interested in development of ultra-powerful optical microscope for unobstructive imaging of live biological samples using the technique of quantum optics, which is what today's talk is based on. Dr. Kapale's research in the area of super resolution has been recognized and featured in the American Physical Society's weekly publication, spotlighting as exceptional physics research. Dr. Kapale is currently his research interest includes quantum error correction, quantum games, and quantum communication. Dr. Kishore is currently serving as the chair and professor at the Department of Physics, Western Illinois University, America, a very distinguished academician and a very sober person. I will call him a man with simple and less words, but high in action. This is what today's speaker is. Welcome, Dr. Kishore.
Thank you, sir. Thank you very much, Bole sir. This is really a very, personal delight and a great honor for me to be able to present this inaugural Professor H.C. Pradhan online memorial lecture. Like Professor Shamala mentioned, I am also happen to be one of the beneficiaries of the work that Professor Pradhan has done as during my bachelor's at Vajay College and during my master's at IIT Mumbai. Both times on the weekends, I used to visit HBCSE and attend the regular lectures that were being held there. And that was, in some sense, life-changing for me. It helped me develop the liking and the passion for physics. So my growth has, a thin thread connected with Professor Pradhan. And so that's why this is, a great personal delight and honor for me to talk about some of my...
Kishore, I may interrupt. Please put your video on.
Okay.
It will be better.
Let's see if I can do that.
Yeah.
So I think I will need to change my setting for that just a little bit.
Okay. Go ahead. Go ahead.
Okay, how about now? Can you see me okay?
Yes, sir, we can.
Okay, but now it's not, let's see, it's not a full screen mode, so that's the challenge.
Sir, after you put the full screen, then share it. The Windows will show two different windows.
Yeah,
One of PowerPoint and one of full screen. So, no, you're on Mac, so okay.
And so, let's see. Let me try this again.
Can come out of sharing and then put it on the full screen and then share.
Okay, now it's in the full screen mode. Let's see how it looks now. Okay, that's much better. Very good. Thank you. So yeah, once again, just going back and reiterating that I am extremely delighted and honored to talk about some of my work. It's not quite recent. The plan here is to touch upon the fundamentals of super resolution and some of the connections of it with my field of research, which is quantum optics. And the two examples that I will be able to talk about today is based on two interesting areas, of course, atom localization and microscopy, which benefit tremendously through the ideas of super resolution. Are you able to see me okay now?
Yes, sir.
Okay, very good. So I think that let's move on. So the first example of application of the super resolution ideas is a prominently used method for creating semiconductor structures or thin film structures, which is atom lithography, where you're depositing atoms one at a time, which are controlled by some sort of a mask. And in this case, we are thinking of that mask as designed through standing optical waves. So that's sort of what you are seeing here in the diagram. Z direction in which is the atoms are coming down, and XY is the plane in which the substrate is located. And XY plane also has this special variation of the electromagnetic field which allows you to choose certain areas to deposit the materials on. And another, of course, very, very prominent and extremely useful application of super resolution techniques and ideas is microscopy. And he is one of the early microscopes developed by Carl Zeiss in 1879 with optics by Abbe. And we all know, if you have seen an optics textbook, it is very difficult to miss Abbe. Abbe had been prominent in early development of the geometrical optics concepts. And then the third example that I have here is something called Heisenberg limited interferometry. I have worked on it personally, but we will not be talking about it today in the interest of time. And what you see here is a beam splitter that has two input ports, A and B. And so the beam splitter allows these two inputs to interfere. We have upper path, which both of these upper and the lower paths have a mirror reflector, so to be able to bring the beams back onto second beam splitter. And the upper path has a phase difference phi. And then you have, of course, because the purpose behind this interferometric technique is to do things at single photon level, and that's why you have these detectors, NA and NB, as opposed to a screen where normally we would try to collect an interference pattern. And so the advantage here is that if you choose your input states carefully, you can actually attain super resolution in interferometric measurements of extremely small gravitational fields, electric field, magnetic fields, and so on. And so, again, I'm kind of trying to allude to the concept of Heisenberg uncertainty principle or Heisenberg limit being more profound as opposed to the standard diffraction limit that we normally ascribe to microscopic resolution. So moving forward, here's sort of the outline. I will give a brief intro to the concept of resolution itself with the standard concepts that can be found in the textbooks, optics textbooks, diffraction limit. I will then connect diffraction limit with Heisenberg's uncertainty relation, as it is commonly found when undergraduate students are introduced to the quantum mechanics in their sort of a very first exposure to it. And then I will also talk about sort of classical tricks that are commonly used to beat the diffraction limit. So then I will go into some of my work that has been done almost a decade or so ago in the area of sub-wavelength atom localization through what we normally term in the field of quantum optics as quantum coherence effects. So I will give you a brief intro to these quantum coherence effects, and then we will talk about their application to super resolution. And then lastly, I will touch upon the field of microscopy itself that can be tackled, or we can develop new techniques for super resolution microscopy with the help of these quantum coherence techniques. And then, of course, I will connect this with a phenomenal work that has been done in the field of biology and biomolecular chemistry to sort of show that when we sometimes attack problems through the fundamental approaches, we tend to gain even more advantageous situations than what is normally thought of. And then I will provide just a brief summary of what we have talked about. So just coming to introduction, we all are familiar with wave optics, and our early introduction to optics is through geometrical optics, where we assume light is propagating as a ray. And when we have, let's say, a lens, two parallel rays coming through a lens, we assume that they meet at a focal point, so just a singular point at which an image is formed. Of course, reality cannot be far from what this picture tells us. Light is a wave, and so focal region is never really a singular point. Yes, the light rays do come closer, but there is a certain size associated with that focal region. And we can, again, of course, ask a question, why? And the answer to that is coming up on the next slide, which happens to be diffraction. So let's go into the details of what diffraction looks like. So it is essentially the bending of light when it encounters a small opening. So A is the width of the opening in a screen, and so light is coming from the left part of the screen here, and as it encounters a small opening, depending on the size of A, which we are assuming here to be roughly of the order of the wavelength or slightly larger, more or less of the same magnitude, then we are going to have the light bend. And as a result, different parts of these openings, you can think of them as independent light sources using Fresnel's or Huygens principle, rather. And then we are going to have some sort of interference pattern on the screen. Essentially, it's a diffraction pattern, which if we were to look at the distance to the first minima, it turns out to be proportional to the wavelength, lambda, the distance between the screen and the opening, and the aperture size, which is sort of the opening size A. And so this diffraction limit, the diffraction pattern itself is sort of the size limit that it appears to be that nature has put on us, right? And that's where sort of the Rayleigh criteria comes about. So let's take a look at sort of a two-dimensional airy pattern that, say, a set of cylindrical lenses would generate when light is coming from a point source. So our ultimate goal here is to look at microscopy. And so here's a point source of light that we are trying to image with the help of an objective and another additional lens. But instead of seeing that, through this combination of lenses, instead of seeing that as a single point, we end up getting this airy disk where we have a central maximum peak, which has, of course, the largest intensity. The intensity drops down as we radially move away from that center point, but you get this ultimate bright and dark fringes. And that is basically what is called the airy disk. And the width of the central peak is called the point spread function, where it is essentially the limit of resolution. And this whole pattern in the two-dimensional sense of it, as shown in, say, image B here, it's called the point spread function, meaning image of a point source doesn't look like a point in the image plane. It looks like a function that's spread out in the radial direction. And of course, we have radial symmetry here because we're trying to image a point source. So trying to connect that with our diffraction limit, the distance to the nearest minima, or the radius of the airy disk, if you will, is lambda d over A, which then, if we connect it with the refractive index of the lens, then it's going to be lambda divided by 2 times n times sine of alpha, and alpha is 2 alpha rather is the angle made by the outcome, the rays that are coming out from the point source with the normal to the substrate there. Right? So I have another picture that will clarify that a little bit more. So looking at diffraction limit, and it's again reiterating what we read as Rayleigh criteria in our entry-level optics textbooks, is that for a microscope that we build that has an objective, that is the collection angle of 2 alpha, then the smallest distance, the smallest object that such a microscope will be able to measure or distinguish between is technically termed as lambda divided by 2 times the numerical aperture. And in most of the microscopic situation, it turns out to be n times sine alpha. That's the numerical aperture of the microscope. N is the refractive index of the material from which the objective lens is built, and 2 alpha is the collection angle. And here's sort of a pictures that show you, depending on the size of the airy disk, the feature size of the pattern that we are going to get, it changes. And the ultimate goal when we are trying to resolve something or look at a very small biological or chemical sample, our goal is to be able to distinguish 2 atoms or 2 molecules that are pretty close to each other. And if they happen to be within that distance, delta x, then we cannot tell them apart as 2 individual independent sources. And if you cannot tell them apart, that means our resolution is limited. Florida State University has this very nice set of tutorials on classical optics, and that's where these images are coming from, and there is a link there at the bottom if you're interested in looking at that. So let's take a look at this slightly more deeply. It turns out we have this Rayleigh limit that's coming to us because of the standard optics and the work of Abbe, Airy, and Rayleigh. But Heisenberg was thinking about this, and he said if we want to be clear about what is meant by a position of an object, for example, of an electron, then one has to specify definite experiments by which the position of an electron can be measured. So he said you cannot just look at something as an instrument that's trying to measure something. The instrument itself, especially in the quantum domain, instrument itself becomes part of your experiment. It is a quantum object in itself, and you have to take into account the full behavior of the system to really understand what's going on. That's where Heisenberg was getting at. And he built a sort of a thought experiment, which is called the Heisenberg microscope. So here's the idea. You have an electron that you're trying to detect. So electron is a quantum object. You're trying to detect that with the help of a photon that's coming in. At the bottom of this, the image here, the electron is going to, of course, scatter the photon, and the scattered photons are going to go, and a part of them would be scattered in all directions, of course, but you are only going to be able to collect a small number of them with the help of the microscope objective. So if the angle subtended by the microscope objective at the location of the electron is 2 theta, and so take half of that angle theta, that gives us the sort of the largest horizontal component of the momentum of that electron is going to be p sine theta. That will be collected by that microscope objective. So uncertainty in the x component of the electron momentum, as it interacts with the photon, it is invariably going to get kicked. And so the maximum kick or maximum uncertainty that arises because of the way microscope objective is looking at it is p times sine theta, which is h over lambda sine theta. And then we introduce the Rayleigh criteria for resolution of a microscope in this situation. So the minimum uncertainty in measuring the position of the electron along the x-axis, delta x, is going to be lambda over sine theta. And so this is how sort of the treatment in the classical or the entry-level quantum mechanics books comes about. And then you combine these two uncertainties, the delta px and delta x, and then you arrive at the product of those to be roughly about h. So this sort of creates a scenario or situation in which it turns out, or we could be thinking the uncertainty relation is heavily dependent on the truthfulness of the Rayleigh criteria for the resolution of the microscope. They seem to be completely intertwined with each other, but this just happens to be a very quick derivation of the Heisenberg uncertainty relation. In fact, as I will show you in a minute, the Rayleigh criteria is not fundamental. It can be overcome. There is no such luck with overcoming the Heisenberg uncertainty relation, of course, right? So let's take a look at this. Where is this Rayleigh limit coming from? And then can we connect it with the uncertainty relation little more deeply than this basic derivation that is commonly found in all quantum mechanics textbooks? So what one has to really look at is something called the angular spectrum of the waves that are emitted by, the scattered waves that are emitted by a point source of some kind. So in this case, we go back to sort of our area situation where you have an opening and the length of the opening is much larger than lambda over 2. Then if you look at the wave vector, the intensity versus the wave vector in the parallel direction to the opening, you can see it is very fine feature, fits nicely. All of those different disks, area disks, fit nicely within the limit of negative omega over c to omega over c. So very sharp momentum spectrum, if you will. As L becomes the same size as lambda over 2, you could see the area disk sort of tries to spread out. Still, major component of it is within negative omega over c to omega over c. But as the length or the opening or the feature that you're trying to measure is smaller than the wavelength, then we start getting a much wider angular spectrum, which then a good chance that some of it might be missed because these vertical solid lines depict what a microscope objective is able to collect easily. And so in the lowest picture here, a major component of the angular spectrum is outside of the negative omega c to omega c domain. And that means we are going to miss out on that. We're going to be essentially neglecting a whole lot of information. And then naturally it leads to loss of resolution. So this is where sort of the beginning understanding of where the Rayleigh limit comes from arises. But since we wanted to connect it with Heisenberg's relation, let's first look at some of the basic mathematics. Again, I'm a theorist, so I cannot help but show the equations. But this part, this is probably my most busiest slide. After that, things get easier and they would be more conceptual. So here's a line source. We're using delta function that is peaked at x equal to x0 to depict the position of a line source at that location x0. And the field that gets transmitted, k is our wave vector. It is done through a Fourier transform of our object, right? So the object is delta x minus x0. You do an integral of that with e to the ikx dx from minus infinity to infinity, and it just gives you a traveling wave e to the ikx0. Or rather, if it's a delta function in the x domain, in the k domain, it's going to be uniformly bright. And so that Fourier transform looks like that. What happens is our classical microscope, like we said, because of the size of the objective, it is not going to be able to accept all of the different components of K. K essentially has many of these components. And all Ks from negative infinity to infinity are equally likely because our source was a very, very thin line source. So the constructed image, because our ability is governed by the amount of K vectors that the microscope objective can collect. So we're going to call it negative K max to K max. And then you reconstruct, you take e to the ikx0, that's the Fourier transform that we are collecting with the help of the microscope, and then you do an inverse Fourier transform of that, and then we get a function of x, which now you can see certainly looks very different compared to our initial line source. Instead of a delta function, now it is a sinc function, sine of omega sine theta x minus x0 over c divided by x minus x0. Now there is of course a factor of 2 there, but that's not all that important. So again, connecting it back to when the opening is less than the size of the wavelength, the because the negative k max to positive k max is essentially very close to negative omega over c to omega over c, a large portion of the airy disk is essentially not captured and lots of information is lost. And so then the source width that we're going to measure is roughly going to be of the order of lambda. This is, of course, not the precise expression for the resolution, but that's the minimum that we get because we are limiting what we are collecting. For students in the audience, and I'm assuming there are some, I have a little puzzle here for you. I have written down here kx. Kx direction is the direction in which we are trying to resolve, and so we're just looking at the kx, the wave vector in the x direction, and it can be written down as, in this situation, because the microscope objective is collecting only omega sine theta over c, it's written as omega sine theta over c squared minus ky squared plus kz squared. So you sort of see, and because this is coming inside a square root sign, kx can be imaginary, and so maybe that has something to do with where the Rayleigh limit is coming from, and so that then allows us to write down the sort of more technically correct expression for the position uncertainty delta x is lambda over 2 sine theta. So this is where mathematically Rayleigh limit arises from. It's our inability, if you will, because of the way we have decided to look at a microscopic system with the help of lenses and so on, we lose out on quite a bit of information. So let's now connect it with uncertainty relation to sort of eliminate this dilemma that the quantum mechanics textbook connect uncertainty relation with Rayleigh criteria. And if I am able to somehow come up with a method to Rayleigh criteria, the proof that I showed you would make us believe that even uncertainty relation is in trouble. But of course, that's not the case. So we need to look at this carefully. So here is a uncertainty hyperbola. Delta x, delta kx is equal to 2 pi. So naturally, it's going to be hyperbola. And if you look at the vertical axis, delta x, the number lambda over 2, which is essentially the Rayleigh limit. And if you extend that all the way to the hyperbola horizontally and then drop a perpendicular on the x-axis, you get 2 omega over c. So you can right now here clearly see that the 2 omega over c width in the delta kx axis corresponds to, because of the uncertainty hyperbola, the Rayleigh limit lambda over 2. Now, if you wanted to measure the position of certain object at a distance that's at an accuracy more than lambda over 2, meaning you want to be able to measure smaller numbers than that, then you have to follow this dashed line, and that leads to some other limit on kx. And so this says that uncertainty relation is more general, and Rayleigh limit is just one specific point on that uncertainty hyperbola. And in principle, if we, staying true to the uncertainty relation, we have ability to go down on the resolution, do better on the resolution, if we are able to collect these other wave vectors that are missed by the standard microscopes. And so that's kind of the idea that all of this presentation that is going to follow hinges on. So here are just some techniques that we have used in the past. The understanding that I gave you here for the recent 1992, that's sort of when I completed my 12th grade. But the super resolution techniques have been around for quite some time. So the fundamental understanding is fairly recent, if you will. So one of the interesting examples of improving resolution is the so-called oil immersion microscope, where you play with the refractive index, increase the refractive index, and because refractive index was in the denominator, that helps you improve the super resolution limit. But if you look at sort of what is naturally available, you're really limited in your ability to increase n. The maximum you can go up to n for all the naturally occurring materials is less than 2 for most parts. So you don't, by doing this in physics, we want several orders of magnitude improvement in whatever we are trying to do, and this doesn't really take there. One other prominent example, though not quite optics, but it allows us to look at samples at the atomic size resolution, which is scanning tunneling microscopy. And of course, it uses the quantum phenomena of tunneling, which allows us to go deeper. So in some sense, if you develop a technique that does not use lenses, is not diffraction limited, then you can improve upon the resolution and look at things more in detail. And based on that, there are actually optical techniques that have been developed, and these are fairly recent, just within the last couple of decades, so-called near-field scanning optical microscopy. So it more or less is along the scanning tunneling microscopy, though, but instead of collecting a tunneling current, you are collecting evanescent waves. And that's where I would like to remind you of this expression for kx that we had, that had a square root. And inside the square root, if your kx squared, ky squared, and kz squared terms are larger than omega sine theta over c squared, then you can get imaginary numbers. And those imaginary wave vectors are essentially evanescent waves. That means they don't propagate. As soon as they come out of the medium that you're trying to image, they actually decay down pretty quickly. And so if you can tap into that with the help of optical fiber tips that are designed to be smaller than the wavelength, then you can measure, you can essentially develop optical microscopy that will give you resolution beyond the diffraction limit. And sort of along the same ideas of tapping into the evanescent waves, we can use the phenomena of negative refractive index materials. It turns out you can build something called super lenses with these metamaterials. These are metamaterials, meaning they are materials developed in the lab. They are not naturally occurring, and they happen to have negative refractive index because the epsilon and mu, both of them, these are the electric permittivity and magnetic permeability of these materials. Both of them are negative, and so it essentially allows you to construct a material with negative refractive index. And what that allows us to do is develop so-called a super lens, which is not diffraction limited, allowing you to tap into these evanescent waves and create high resolution images. So this is one example here that we can see. So those are now sort of standard classical techniques that that existed even before this deeper understanding between the uncertainty relation and Rayleigh criteria came about. And so in the area of quantum optics, there were efforts going on figuring out the location of an atom. Of course, the goal for quantum optics is understand light and matter interaction to the deepest level, and then use it to your advantage in understanding either the atomic properties a lot better than we can do otherwise, or understand the light properties with the help of atoms as your measurement devices, if you will, or you want to be able to use one to manipulate the properties of the other. And so it turns out sub-wavelength resolution was not a foreign thing for quantum optics to begin with. It's just that these two things were not really put together in that context. So looking at the sort of going into the details of some basic understanding of atom-light interaction, let's pay attention to sort of the phenomenological description that almost all the physicists are familiar with always. It's the Einstein AB coefficients. That's our intro to laser physics to begin with. And so here are two or three different scenarios in which the Einstein AB coefficients come into picture. So if you have, let's say, a atomic entity with two levels, EV and EC, with the energies EV and EC, and if you bring in a photon that has the energy that is nearby the difference between these two energy levels, then there is going to be an atom-light interaction happening. The presence of the light field causes the atoms from the lower level to absorb the light and jump to the higher levels. And the absorption probability is given by Einstein B coefficient, B n n prime. N and n prime are just the labels of these two levels. And n is the population in the ground level, and UV is sort of the density of the electric field or the light field that's present. And then h nu is the energy of a single photon. So nu is just the frequency, t is the temperature. And so that gives you the intensity of, in some sense, some measure of the spectral density of the light coming in. Spectral density meaning intensity versus the frequency. And so that's one phenomena where Einstein B coefficient comes into play. There is, of course, spontaneous emission, which is commonly absorbed. If your atom is excited to begin with, it's going to emit light, depending on how many atoms you have sitting in the upper energy level. And so Einstein A coefficient governs that. And the probability is A times the number of atoms in the excited state times the energy of the photon h nu. And then you have another interesting phenomena that Einstein theorized needs to exist to find sort of a detailed balance between light matter interaction at the two level, which is the induced emission. So meaning in the presence of one photon, if you have an excited atom, you are going to cause that excited atom to emit again in the same domain. And that is, of course, the principle behind what we call stimulated emission, which leads to the generation of lasers, which are so prominent these days, right? We cannot function without lasers. In our everyday instruments, we have lots of very commonly used device there. So, Einstein then went on to essentially derive Planck's law using all of sort of the stationary equilibrium, the probability of atom going upwards, right, making a jump from the ground state to the excited state should be equal to the same as it making jump from the upper state to the ground state. And so the first coefficient for the induced absorption matches with the addition of the other two. And so that's the rate equation. Again, we don't need to go into the details, and I'm not going to be solving that equation. In most cases, we assume the number of atoms sitting in each level governed by the Maxwell-Boltzmann distribution. So Eg is the energy gap between these two, and so you get the Maxwell-Boltzmann distribution atoms. But if the system is at a given temperature, of course you have bosonic systems and fermionic system, which would not follow that. But for most part, this idea works. So this is sort of a phenomenological approach to light atom interaction. And one rule of thumb that we can capture from here is that if the light is present, that light can do either induced absorption or induced emission. So if the light is continuously present and you have a two-level atom, you actually get the population cycling between the two levels continuously. This cycling is something that I will be using later on for one of our proposals that I will be talking about. So the first phenomena, induced absorption and induced emission, in the presence of the external light field, actually generates very interesting scenario that is commonly missed when we are talking about the laser physics, but it's extremely important in the field of quantum optics. So let's kind of going into just some very basic details without going into the mathematics of how we deal with atom light interaction in the quantum domain is in the so-called electric dipole interaction. And here's the electric dipole interaction Hamiltonian, just the interaction part, which is negative dipole, electric dipole of the atom when it is between, when electron is making, let's say, a jump between the two nearby energy states multiplied by the electric field at the position of the atom. So these is the atomic dipole moment operator, and you can evaluate that using the quantum mechanical description of the two states and just expectation value of ER. Essentially, that's what the atomic dipole moment is, and R is the center of mass position of the atom. And so this interaction Hamiltonian is approximate, of course, right? Because we are not including magnetic field. Remember, light field has both electric and magnetic fields. And this is also valid under long wavelength approximation. That means we assume that the size of an atom is extremely smaller compared to the wavelength of the electromagnetic radiation. That, of course, turns out to be an advantage in the field of microscopy if you are trying to increase super resolution. And of course, electric quadrupole and magnetic dipole interactions are smaller by a factor of the fine structure constant 1/137. So they are neglected here. Only in situations where the dipole interaction vanishes because of the selection rules between the energy levels. If for some reason the electric dipole transition is forbidden, only then we encounter electric quadrupole and magnetic dipole interaction. So how does this all relate with atomic microscopy? So we of course talked about the Heisenberg microscope, where the smallest distances that you can measure between objects is going to be roughly of the order of. The question then is, the atom is very, very small compared to the wavelength. So if somebody gave us a standing wave of light, can we figure out where in that wavelength region atom is located? Because it's going to interact, right? There is a little bit of a hint in this E of R. So in some sense, the atom is able to sense the electric field at its location. And so if that's the case, there is sort of inherent position dependence built into the interaction Hamiltonian. And can we exploit that to measure the position of the atom? That's sort of the question that one can ask. And so we are then going to generalize that question and simplify it a little bit, which is how to localize an atom in a standing wave. And so just kind of to give you a short history of some of these work in the area of atom localization, you have a cavity in which you can, this is an optical cavity. You have two mirrors within which you can create a standing wave, very, very, very productive field, and has allowed us to understand atom light interaction at a much deeper level. But another application of that to atom localization has been through 2 or 3 different methods that I'm just listing here. Something called a quadrature field measurement. So you measure the field of the cavity field after the atom has had chance to interact with it. And the cavity field then contains some information about at what location did atom pass through that cavity. So that has been done. In fact, Professor now from Caltech has actually created movies of atom going through the cavity field, and he can tell exactly which parts of the cavity field he interacted, the atom interacted with. Another very common technique is called Ramsey interferometry. This is Norman Ramsey, who won the Nobel Prize for his work on light atom interaction at the microwave range of the electromagnetic spectrum. So he, the interferometry method is based on his ideas there, and the way to localize the atom is after it has interacted with the cavity field, which has intensity that is position dependent. You measure the internal state of the atom, and then you're able to figure out what's going on. And then another thing that one can do is somehow create the atom light interaction and choose your levels carefully, that you can actually get the atom to emit a photon after it has had interaction with it. And that photon then would carry that information of E of R, right? The position dependency of the electric field of the cavity field. So these were some of the early history of this work. And I'm going to now talk about spontaneous emission specifically, to sort of illustrate the tricks that we have at our disposal in quantum optics. There is no reason why we only have to atoms. 2-level atoms are simple. You have the spontaneous emissions from the excited level A to ground state level B, and you get a spectrum which is intensity versus the frequency. And you can see it has a certain width, and that certain width, that's sort of the standard emission spectrum of a two-level atom that is excited to begin with. It turns out you can do a lot more interesting things if you allow or you take into account the naturally multi-level nature of the atoms, and instead of targeting just two levels, you target, say, three of them at a time, right? People have, of course, done work with many levels at a time. I have done some work where we had about 5 or 6 levels, atomic levels, and dealing with the phenomena there. But the simplest extension, if you will, is 3-level atoms. And what we have done is I have added this level C, and the level C and level A are connected with another electromagnetic field, so another laser field that matches the energy level difference. And so what it does is when that field is present, it drives the population between level A and C continuously. And so on, that then naturally modifies the spontaneous emission happening from level A. And it turns out you get, instead of a single peak in the spectrum, now you have 2 peaks, a doublet that is separated by a certain distance. And this is called Outler-Towns doublet. Towns is the same Charlie Towns who won the Nobel Prize for invention of the laser. So what happens is, if you were, remember I gave you the expression for the interaction Hamiltonian. Hamiltonian within the sort of the 3-level system can be written down as a 3x3 matrix, which you can diagonalize. And once you diagonalize, you get these states, which essentially means in the presence of C and the electric field, A essentially gets split by a certain amount, which is dependent on the dipole moment AC as well as the electric field strength. So you can control how much that splitting is. But now this excited state, because it's split into 2 components, both of which are going to decay, and at the central wavelength, those 2 decay pathways are going to interfere, and you get a destructive interference at the center, and that's why you get sort of this splitting of the spontaneous emission spectrum. And so you have, in some sense, generated a quantum interference phenomena, or it is also termed as atomic coherence effect. And so we take these ideas and apply them to microscopy. So here is instead of applying just a standard laser field, we apply a cavity field, which is a standing wave field, meaning it has a spatial modulation of sine kx. And so that means it has position dependence. That means the spontaneously emitted photon would also have the position dependence in it, and that will then naturally allows us to tap into. So there's the state picture that we talked about has the splitting of the excited state is position dependent, and we can tap into that. So if you are able to collect the spontaneously emitted photon, the D here is the detector that allows us to look at the spontaneously emitted photon. It carries then position information. So one of my other mentors when I was at Texas A&M was along with, of course, Dr. Marlon Scully, who happens to be a graduate. He did his PhD work under Willis Lamb, and then Professor Zubairi was another one of my mentors there. So he has done some a whole host of work in this area of using spontaneously emitted photon for localizing an atom in a standing wave. Localizing in a sense meaning, you are trying to figure out post priori what was the position through which the atom passed through. So we took this idea further, and we wanted to see if we can solve the most fundamental problem in quantum mechanics, which is measure the wave function of an atom, right, using these spontaneous emission spectrum. And it turns out it is possible to do that. So we again take the same idea, but now we are trying to measure both the position distribution as well as the momentum distribution of the atomic beam that is going and interacting with this standing wave field that's arranged in the x direction, right? So the atom is passing through, depending on where it interacted, the spectrum of the spontaneous emission is going to be dependent on that, and can we trace that information backwards to measure it? And it turns out it's possible. Measuring the position and momentum distribution of the atom condition on the detection of spontaneously emitted photon gives both the amplitude and phase information of the center of mass wave function of the atom. So it is possible to do that. Of course, as quantum mechanics says, one measurement on one atom is not going to tell you anything about the state of the system, and you were going to get multitude of measurements. And this was work that was published, I think, soon after I got my doctorate from Texas A&M. But it's sort of, handles this one of the very foundational problems in questions, if you will, in quantum mechanics. It turns out spontaneous emission is difficult to measure. It is the light emitted is scattered in all directions, and so you really need a 4-pi detector, which are available experimentally. But it's a difficult thing to do. Naturally, as a theorist, we can ask a question: can we do something simpler when an experimentalist complains? That's not easy to implement in an experiment. So this is where we go. We're using quantum coherence effects, the workhorse of quantum optics, and I illustrated sort of the quantum interference effects of manipulating the interaction of the upper level with some other third level. We can manipulate the spontaneous emission spectrum because it creates interference effects. Here's another very, very interesting interference effect when we add a third level in the mix. So we are going beyond just 2 levels. We are again going to deal with 3 levels. So the phenomena itself is called coherent population trapping, meaning we are using light field and coherent light matter interaction. Coherent meaning it's happening at a specific wavelength, connected with specific energy levels of an atom. We are able to trap atomic population in certain states. So here's how the situation works. We have level 1, 2, and 3. 1 is the excited state. 2 and 3 are the lower level states. So you can think of them as sort of hyperfine sublevels of an atom. And then we have the standing wave field is this omega S. Gamma S and gamma P are the spontaneous emission from level 1 to level 2 and level 1 to level 3 respectively. And delta is the detuning. You don't always need to have your frequency perfectly match the energy level difference. It can be slightly detuned, and that detuning means just the frequency differences, atomic frequency versus the light frequency. And what I mean by atomic frequency is the energy difference E1 minus E3 divided by H. So that's just the term. So detunings are actually useful, and it turns out if you define this quantity omega, it turns out you can diagonalize this Hamiltonian, and this specific state, which is a linear superposition of level 2 and level 3, meaning it's a mixture of these two, at steady state, when the atom and light has had enough time to interact with each other after many spontaneous emission decays have happened, the population, doesn't matter where it starts to begin with, it is going to get trapped in level 2 and level 3. So now we have this nice steady state, which is called the dress states, which is the eigenstate of the Hamiltonian system. So you can actually take that matrix, find its eigenvalues and the eigenvectors, and that eigenvector is very simply just a linear superposition of the bar 2 states, meaning the atom doesn't like to stay in the upper state. It stays in these 2 bottom states. And that has a variety of application, even in the area of quantum information. But it also leads to very interesting scenarios because your population is trapped in the lower 2 levels. Even these lights, more or less matching the energy level differences with the atom, both of those lights do not absorb. So if you have a strong omega S field, the weak omega P field does not get absorbed. That means you are using one field as a control, and so it's electromagnetically induced transparency. So you can make a material that is normally not transparent because of the 2 levels matching the energy spectrum. The material would absorb light, but the moment you bring in the second field, the atoms actually become transparent to both the fields, and that has tremendous applications as well. And it also leads to lasing without inversion. Even though your populations are at the bottom two levels, you can generate lasing without really populating the upper level, because normally that's what you need. You need inversion for laser action to happen. Not in this scenario. And so we did Professor Agrawal, who was the director of PRL for quite some time when I was going through my bachelor's and master's. He is now currently at Texas A&M. And before that, he was at Oklahoma State University. So, he was also intensity of the two light fields. As our intensity of the two light fields, as R increases, the pattern that you get here is more and more refined. And that means if these peaks are the locations where the atoms has been going through, and the width of these is much smaller than the wavelength, and that allows you to do deposit. For example, if you're doing atom lithography, you can deposit a very refined pattern that is smaller than the wavelength that you're using, or you can localize an atom that is at much smaller wavelength. Of course, there's a price to be paid because of uncertainty relation. You cannot escape that ever. And so what happens here is we have to look at the momentum spread, and the momentum spread turns out to get worse as this R, which is a ratio for high resolution, it makes the momentum spread worse. But that's a price to be paid. You can figure out experimentally how much price is affordable, and then you decide the value of R, and that is going to give you the resolution that we want. And just like in the introduction, Professor Bole mentioned one of my work being implemented by Bill Phillips, who won the Nobel Prize in 1997 or 1998 for laser cooling. They did some of the experimental implementation of my other work came a little later. Our coherent population trapping based atom localization idea was also implemented experimentally in rubidium-87 atoms. So here's the energy level they use. So you can see real atoms are even more complicated than the three levels that we theorists proposed. So they actually have 6 levels playing at the is exciting 3 different sub-transitions here, and that makes it for interesting. And then again, the resolution that they got was lambda over 8, so certainly much beyond what Rayleigh limit allows, and it's a very nice implementation of our work. If we are interested, there is a simpler account of this available at this physics news articles that come sort of on a weekly basis, explaining the details of this work, and then our work also as a sort of a foundation behind it. If you are interested in learning more about subwavelength atom localization, volume 458 of Progress in Optics, which is a volume that's published every year for many years. This one came, I don't remember exactly the year it came out, but I have a full chapter on subwavelength atom localization in this volume that goes into some of the history and the details of the recent method. Goal today is to get to microscopy. So in the next 10 minutes or so, I will talk about subdiffraction microscopy. So here is sort of the idea of taking this position-dependent atom-light interaction, and then instead of just lithography, generating subwavelength patterns of atoms, can we actually see it? And then if we look at the some of the different manipulations that we added onto CPD allow us to go to resolution of lambda over 2000. That means if you are playing with wavelength of about 500 nanometers, you get about 2.5 nanometer, or even less than 0.25 nanometer resolution with the help of these ideas. So you get to actually sub-nanoscale resolution with the help of the methods that we have come up with. So what the ideas that we used are the standing wave field, of course, which is this modulated intensity that we see here, and the modulated probe field. The probe field, which is just uniform here, can also be modulated in intensity. Population of this CPT state, which interact with our system would look like. That's how big its point spread function would be. So a single point looks that big at circle, but our over 100, very entry level calculation that we did in the already 2 hours of improvement in the super resolution there. And again, the idea is increasing R offers more of these advantages. And then we added several other interesting sort of quantum optics techniques, is sort of a harmonic modulation of the field that we apply. And what I mean by harmonic modulation is shown here. You have the standing wave field for the omega S, which is connected with level 1 and level 2. So omega S sine kx. And then omega P, the probe field, which is supposed to be slightly weaker, we manipulated at certain frequency. Its intensity is manipulated orally at cosine nu. It oscillates with time. And then we, of course, the population would have those sort of Fourier components at different frequencies. And if we individually measure those Fourier, actually ends up improving our resolution. So the graph A here is the point spread function, and you can see it's progressively getting smaller and smaller. And the circles in the KXKY space are getting progressively over 100. Blue is the DC term in the population of the second level. Green is the coefficient of cosine 2 nu t, and black is the coefficient of cosine 4 nu t. So if you progressively sample these Fourier components in the population, then you can go up to lambda over 2000 resolution. That means we are progressively getting a much better, clear idea exactly where this object is located. Lambda over 2000 becomes actually sub-nanoscale resolution. To sort of connect with the biochemistry work that has been done and that actually received Nobel Prize in chemistry in 2014, I would just like to, in 1 minute, illustrate a new degree of freedom that light has. We, of course, are familiar with polarization, which is what our ordinary light is. You can have left circularly polarized light, right circularly polarized light, and so on. But even beyond that, it turns out light also has an angular momentum degree of freedom. So the pointing vector, if it is going around the beam axis, then that laser beam happens to have an orbital angular momentum, and that is also a quantized degree of freedom. That means you can have specific integer orbital angular momentum 0, 1, 2, 3. And if you wanted to sort of understand, it is sort of a helical phase structure. We are familiar with plane waves, where if you take a laser beam and cut it, at all points along that intersection, the phase of the wave would be exactly the same. But you can have corkscrew type phase structure, sort of like a screw at OM1. If you have double of those two intertwined phase structures, then you can have orbital angular momentum of 2 and 3 and so on. So very interesting structures. If you look at the intensity profile of these, they are naturally position dependent. You have a tiny hole in the center where there is no light passing through. It's sort of like the spiral staircase. You cannot have stairs in the center. That center just sort of supports the spiral staircase. And so that spiral structure imposes a zero intensity at the center. And that has been something that has been used by low intensity. And then, of course, you have the omega P has the Gaussian structure, as well as on top of that, we have the harmonic modulation. This was coherent population trapping. It has certain limitations. And so without going into the details of how we overcame these limitations, I'll just tell you that we could take these 3-level effects and mimic them onto 2-level schemes by having 2 light fields simultaneously interacting with a 2-level system. So I think that's all the detail that I'm going to go, but it allows us, essentially generate, again, CPU-based microscopy, which then looks very similar to the the biochemistry work that I will show you on the next slide. So the idea works, and then we are able to get resolution that is actually much better than what they were able to do, in the work that got the Nobel Prize. So I'm going to skip next 2 or 3 slides. They're kind of detailed, technical, but the idea again is to show that we get nanometer resolution by this. So just to illustrate connection with biochemistry, Nobel Prize in Chemistry in 2014 was given to Eric Betzig, Stefan Hell, Morner. I will show you some of the work that Stefan Hell did on the next slide for the development of super resolved fluorescence microscopy. They, of course, were heavily dependent on specific molecules that fluoresce in the green range of the electromagnetic, the visible light, and those green fluorescent proteins was sort of the light generating mechanism that they tapped into to do that. So let me just take 2 or 3 minutes to illustrate the stimulated emission depletion idea. The idea again is similar to what we were doing with our 3-level atoms. You have 2 light fields that are coming in, and one of the light field has this donut profile. And with the help of them, by superimposing the Gaussian beam with this donut profile, they make sure that the fluorescent proteins in that small donut hole are the ones that are active, giving you a much finer point spread function. So that's the idea. So they apply the light field. So one light field absorbs, there is some fluorescence happening, and the stimulated emission coming from only the tiny portion here that sees one of the fields and not the other field, and it gives you high resolution. So Stefan Hell, who is right now at Max Planck Institute for Multidisciplinary Sciences in Göttingen, Germany, he received the prize winners for 2014. And here's sort of the idea. Again, we don't need to go into the details. The idea is based on using the donut-shaped hole of the orbital angular momentum degree of freedom of light, which is naturally a feature that is smaller than the wavelength. Because that feature is smaller than the wavelength, it allows you to go beyond the diffraction limit. The super resolved microscopy work that is being done right now across different areas, biochemistry, chemistry, even quantum optics and physics, is so-called point function engineering. You want to get that point spread function as small as possible. So just to kind of illustrate some of the prominent techniques, confocal microscopy gives you about 200 nanometer resolution. For trying to collect as much light as possible in all different directions. So you kind of have a cylindrical detector instead of a spherical detector, and that lets you go from 200 nanometer to 90 nanometers. Then you get to about 20 nanometers. If you look at the point spread function here, right, in this last panel, lambda over 2n sine alpha, that's our Rayleigh criteria. On top of that, we add factor. The STED microscopy of Stefan Hell adds this factor 1 over square root of 1 minus I over IS. So IS is sort of the saturation intensity. I is the intensity that is applied. In our case, we are able to remove that the square root. That means we get another order of magnitude, couple of orders of magnitude improvement, and we can go to sub-nanoscale resolutions with our technique. So quantum optics, when you go into the detailed fundamental light-matter interaction, you can do a lot better than these sort of the simple tricks that were played by microscopists in the several different examples that I showed you. So coming to the summary, Heisenberg's uncertainty relation is the fundamental limit for high resolution. Even though Rayleigh criteria is posed as a limit, it is not a fundamental limit to resolution. It can easily be surpassed. We talked about several classical techniques, and I told you their application for atom localization, atom lithography, and microscopy. And the trick is to use the special dependence of light-matter interaction, the position dependence that naturally exists, coupled with some kind of a nonlinear phenomena. The atomic coherence effects that I mentioned are inherently nonlinear because you have one light field affecting the response of the atom or at the wavelength of the other light. These are coherent population trapping and coherent population oscillations. And then this sort of connects with some of my later work on Heisenberg limited interferometric high resolution measurements, which are even more deeper quantum tricks that one can play, but we don't need to go in there. Maybe that's an opportunity to talk at some other time. But thank you very much for listening, and thank you very much for giving me this opportunity to speak with you.
Thank you, sir. In the chat box, there are no questions.
Okay.
But
I will.
YouTube, there may be. Professor,
can radioactive element be used for CPT? Yes. So we are tapping into the electronic degrees of freedom when we are doing CPT. So if the material is radioactive, that will change the hyperfine structure, might be a little bit, but again, that's not very stable. So if you can tap into electronic degrees of freedom without having to worry about the nuclear degrees of freedom, you can use radioactive material. There is no restriction as such. In quantum optics, normally, because things are simple, we use the first column of the periodic table. Like I gave you example of rubidium, cesium, strontium. These are commonly used atoms because it's single electronic systems, very easy to understand. And the lasers for all of those atoms are available. So availability of lasers is another issue that one has to deal with based on what material you're trying to find.
But because of this development, probably the nanotechnology will be flourished.
Yes, so what I envision, and I think there is one other recent progress in super a result and train it so that it can eventually computational algorithms reduce this point spread function. So that possibility is there. In computational microscopy existed before the AI methods came about. So that availability is. But in this case, it is still a visualization tool. I mean, if you wanted to talk about implications for nanotechnology, this is still a characterization tool and we use graphic method. You can build nanomaterials that way. But most the currently